Hello everyone, welcome back. In this lecture we're going to be discussing about some important concepts regarding protocol verification. In a typical chip design, we typically deal with many asynchronous interfaces and how the protocol between different entities get followed correctly. How do we verify them? Assertions play an important role in verifying protocol across the asynchronous interfaces. So let's talk about basic concepts. We have a master and we have a slave. Okay? Master sends a request along with the data to slave, and slave responds with a grant. Okay? Now this is a very simple request data and grant protocol. Um, very simple. This protocol can be very complex depending upon which handshake mechanism or which design technique has been used. However, the idea to discuss the assertions here to make you the concepts clear so that you can write assertions based on your requirement. All right, so let's talk about further. Make it a little bit more interesting and complex. Master is running at its own clock and slave is running on its clock. So we have a asynchronous interface where master sends a request and data at its clock and slave sends the grant back to master at its clock. So let's call master clock clock M, slave clock clock S, and the question is here, do these interface signals follow correct protocol? Or in other words, how do we make sure that the request is asserted or de-asserted after how many clock cycles of data is stable? Okay, or vice versa, depending upon how far master is sitting from the slave. So there may be timing constraints involved here, that how the timing analysis guys wanna time this. Typically it's a asynchronous interface, so they just can tell you that okay, it's gonna take 3 or 4 clock cycles for the data to reach from the master to slave, so you can time it accordingly. However, that timing aspect is out of picture here, whether it's synchronous or asynchronous. At the RTL verification level, your goal is to make sure that whatever protocol is specified is followed accurately. So let's talk about here. Let's draw some diagrams. Clock M, master clock, is running at some frequency and data is changing at a master clock, and then the master sends the request. Now one protocol or one specification or requirement, one can say that the request should be asserted only after a certain number of clock cycles the data is stable. Okay, in this example, let's say request must only get asserted by the master if the data is stable for 3 clocks. His data should not change for 3 clocks. If the request gets asserted within 3 clocks, means we have a problem. Okay, so how do we detect it? Okay, another scenario can be at the slave side, that slave is running at its clock, which is slower than the master clock, and the slave assert or de-assert the grant based on the request. Okay, so master de-asserts the request and one can specify a requirement that the grant must have to be de-asserted within n number of clock cycles of request gets de-asserted. In this example, let's talk about the grant must get de-asserted after the 2 clocks of the request gets de-asserted. Very simple. Okay, you can make it more complex. Another scenario at the slave side can be that the slave is running at its clock, and the request, what slave sees, it should not get asserted within the 2 clocks or within X number of clocks of the slave clock. Okay, so in this example, the request which slave sees at its end, the request should not get asserted within 2 clocks. Okay, so fairly simple requirements. And how do we verify? How assertions can help here. So let's take very first diagram. From the master side, the request must get asserted only after the 3 clocks data is stable. One can write modules, and one can specify parameters which can have different value at the binding time. Here, let's define a parameter called num cycles 3, and let's try a very simple assertions. Very simple assertion. Assert property at the passage of the master clock. Data is changed and signal request should not rise, okay, within number of clocks. Very simple assertions. Now, in this assertion, do you notice any problem? Well, this assertion is going to work all the time. Essentially, you don't want to get this assertion trigger when you are in reset, or when your block is in reset, or let's say slave or master is in reset. So how we can tweak it a little bit? We can disable this assertion if there is a reset. Okay, so here I'm assuming that it's an active high reset. You can change it to active low, or synchronous, asynchronous, whatever you want to. So idea here is to disable the assertion if we are in reset. Another interesting thing appear in very complex chip verification projects or designs, that you don't want to trigger all the assertions at the same time. Otherwise, it's quite difficult to debug. So you may want to turn them on one by one, or one type of assertion you may want to turn on and then debug it, and then turn on another kind of assertion and then debug it. So to get that thing going on, we can define these assertion properties under guard bands or if defs. So here, let's say if def check request data. This type of assertion properties only I want to check. At the time, if I define check request data while I am compiling the design, only this kind of property will get compiled, or will get effect at the runtime. Okay, the if defs are very handy and very useful for putting guard band against the different properties. Very helpful in debugging. All right, now let's take a look at the slave side. Okay, the grant must get de-asserted after 2 clocks of the request get de-asserted. Okay, same way we define a parameter, number of cycles 2 for the slave, and we write a very simple assertion property. Okay, and at passage of slave clock, if the request goes down, fell is a system SVA, system Verilog Assertion keyword, then between 1 to number of clock cycle, grant should go to 0. This is one way of writing. You may encounter different ways of writing simple assertions. There can be different ways of writing assertions. All right. Now, same way, if my block is in reset, I don't want to trigger those assertions. So I disable those assertions or those assert properties when I'm in reset. And same way, I define the guard band against that type of property. If def check grant follow request. Okay, I define it under if def, so it acts as a guard band. Good, very nice. Now let's make situation a little bit more interesting and complex. So I have a one master, okay, and one master is communicating with 3 slave instances. Okay, these slaves may be may have the same module and different instances, or different modules and then their instances, does not matter. For the concept here, the master is communicating 3 slaves. So how do we have to write 3 copies of the same assertion, or can we do much better task here? So idea is to reuse as much as possible. Okay, so we write assertion properties or assertions once and make reuse those assertion properties many times. Okay, so for that we define all the assertion properties or assertions under one module. Okay, or you can split one type of assertion in one module. So let's say you have 6-7 protocols to check. So you may define 6-7 assertions in 6-7 modules, or you can write all the 6-7 assertion properties in one module. Depends how you want to structure. But the concept or idea here is to define assertions in one module. So let's say I define my assertions. Okay, this is my module name under a module with the clock, reset, select, request, grant, and data. These signals I'm going to be using inside my module assertion. It's a same way as you write the Verilog modules or system Verilog modules for the design. Good. Define the parameter. I left it here the default value. You can assign the default value of the num cycle in the assertion module. And since now we have interesting situation, okay, same master is communicating 3 slaves. So if it sends signal request, is gonna be going to all the slaves, and all the slaves gonna be responding at the same time. However, we don't want that, so we want to select the different slaves. So master selects different slaves, and then the request gets sampled by the slave. So in other words, if master wants to communicate with the slave 1, master sends the select signal, okay, to slave 1, and request is high, and then the slave samples both of the signals, says okay, I'm getting the request M from the master, and master is giving me select signal. Okay, so master wants to talk with me, okay, or communicate with me. So slave 1 is active or responds, while the slave 2 and slave 3, they don't respond because master does not assert the select S2 or select S3 signals. Okay, so little bit of tweak from the if we want to reuse the assertions which we discussed in the previous page, on the previous page or previous slide a few seconds back. We create an internal request signal, which is nothing but an AND of the request and select. Good. And the same assertions which we discussed earlier, we can reuse. Okay. So instead of, notice here, instead of request, we are using request underscore int signal. Good. And you can put the another second assertion also in the same module. So this is just to show one example. Okay, you may have 10 different assertion properties in one module. All right. So we have written assertions or assert properties in one module. Now next task, how we wanna make use of this module for different slaves or different slave instances. Here comes the binding part. Okay, so we bind the same assertion module to different instances of the slave. Okay, and we write another module which is a bind module name, and then the bind module name. Let's say I want to bind assertion to the slave 1. Okay, so bind module name, and then bind is the keyword, and then this is the instance from the chiptop.dot.slave1. This is the instance hierarchical path of the slave 1, and then the module name where I have written my assertions. So 3 things here: bind keyword, which instance I'm gonna bind, and my assertions module name. Good. Now if I wanna change the number of cycles, I can change it. I defined the parameter already. So let's say I wanna change number of cycles from the default value to 2 for the slave 1. So I can change it here, and then the bind instance name, or in other words, bind modules instance for the slave 1. So bind slave 1 to my assertions, and these instance names should be unique. Okay, then clock, here I am referring those assertions with respect to clock of the slave 1. Good. Reset, select with respect to the select signal for the slave 1. Request, master sends the same request to all of them, and the grant with respect to the slave 1, grant underscore s1, and the data, which is common. Okay, data bus. So this one module, okay, bind module, let me be very specific, which binds my assertion to the slave instance. I can define it that way. Now similar way, I can write another bind module to bind the same assertion module file with slave 2 instance. Okay, the module name, bind module name, bind my assertions, slave 2, bind is the keyword, and hierarchical path to the slave 2, which is chiptop.duty.slave2 per se. Then my assertions module name, and here let's say for the slave 2 I want to change the number of cycles, which is 3. Maybe the slave 2 is sitting very far away from the master as compared to slave 1, depending upon the chip layout. Okay, so I would like to change the number of cycle to 3. Okay, so I can do it here 3, then bind slave 2 to my assertions is the bind slave 2 instance name, should be unique, and then clock, would like to bind to the slave 2 clock underscore s2, reset, and they select with respect to the slave 2 select underscore s2, and the request, master sends the same request underscore m, and the grant, slave 2 sends the grant signal, grant underscore s2 back to the master, and the data which is common. So as you can see here, for each instance we define one bind module. So if you have let's say 80 slaves or 100 slaves, you may have to write 80 or 100 instances if you want to change the parameters here. If you do not have any such a requirement where the different slaves would have different parameters, then you can just bind to the module slave module name, and then the tool will figure it out automatically, all the instances. But if you want to do parameterize, want to change different parameters, you have to do one by one. So 100 slaves, 80 slaves, 80 bind module instances, which is easy, but you don't have to write the assertion definitions or assert properties 80 times. No, you write it at once and bind it as many times as you want. Isn't it beautiful? It's perfect. Very easy. All right. Now, one more thing, which is simulator specific, that you may have to, depending upon what simulator you are using, whether Synopsys, VCS, or Cadence, NCSIM, or Questa from Mentor. Depending upon that, you may have to check the tool vendor's manual. Here I'm talking about specific to Synopsys VCS simulator. You might have to give VCS underscore SVA underscore bind this plus equal to the bind module name. Okay, so here bind my assertions slave 1. I did write one module, so I have to give simulator instructions to compile that bind module. Okay, so in Synopsys VCS we used to do this way. VCS underscore SVA underscore bind plus equal to bind module name, and as many slaves I have, or as many different bind modules I have, I just keep adding those. Okay, and then compile it and run it, and hopefully you will see the assertions get triggered, or you will see in the assertion window or waveform window you can verify. Good. Now, one another important thing which is very handy in debugging the assertions is to have a assertion control, or you can write a assertion control Verilog file in which you can put some guard bands. Let's say if you want to check only check request data. So you have defined the guard band and you write it in assertion control file. In the initial block, at the very beginning, you want to turn off all the assertions at the duty top level, or you can specify the instances what assertions you want to turn off, and you wait for some time. If you think that okay, at this time different assertions get fired, so I should wait for some time, and then after that time I enable the assertions. So here ITF is nothing but the interface. You may have a different mechanism, or you just simply use wait nanosecond, or whatever your environment is specified to wait for some time. Okay, and after that you enable globally the assertions, and then you can turn off one by one the selected assertions, or asserts all the assertions under one instance. For example, here in this example, I don't want to turn on the assertions on the slave 3. So I am turning off assertions on the slave 3, all of the assertions, and just want to focus on the slave 1 and slave 2 assertions. Assertions control file is very handy when you need to debug hundreds of assertions. All right. So thank you very much, guys. I hope this was quite informative session for you. If you have any suggestions or any queries, if you would like me to do any specific lecture on a specific topic, please leave me a message. I will try my best to do something based on your request. All right, have a wonderful day, and don't forget to subscribe.